All right, everyone, so welcome to my review. I am going to start with going over valence electrons, and then I'm going to go into why different kinds of bonds occur, and then the naming and formula writing rules, and then finally finishing off with our chemical equations and how to figure out if they are balanced or not. So in order to understand everything that we're doing right now, we really have to take it back to the valence electrons. So here I've inserted an image that shows our first three rows of elements in the periodic table. You can see hydrogen right here being first. Hydrogen has number 1 on the periodic table, so it has 1 electron, and therefore it's only got 1 electron in its outermost shell, which we can see right here. Okay. If we look at helium, helium's shell is full because the first shell for our electrons can hold only 2 electrons in it. So helium here has a full valence shell. So what that means is that hydrogen is actually going to want to lose 1 electron in order to empty out its shell. And so hydrogen, because of losing that 1 electron, is going to end up as an ion that has a positive 1 charge to it. Now, if I look at lithium and sodium just below hydrogen, those two are both in the same column as hydrogen is. And you should notice that they also have only 1 electron in their outermost shell. So although lithium has 3 total electrons, he's got his first shell full, and then the outermost shell, the valence shell right here, only has 1 electron on it. Sodium also, even though it's got more electrons, all of the shells inside are full. His first orbital is full, his second orbital is full, there's 8 in that one, and then there's 1 valence electron. And so in order to become stable, these guys are going to lose that 1 valence electron. As a result, they have 1 more proton than they do electrons. So lithium is going to get a positive charge to it of positive 1, and sodium here is also going to form a positive 1 cation. So that's why they do that, is because they are more stable by making sure that whatever shell is the outermost shell is full, and so they lose 1 electron. Now, the trend continues. If I look at beryllium right here, beryllium has 4 total electrons, 2 of them in the first shell right here, and then 2 in its second shell. Well, that second shell is not full. So he is going to lose 2 electrons because otherwise it would take more energy to try to gain 6 more electrons to finish off that shell with the total 8. It takes a lot less energy to lose 2 electrons, so that's what he's going to do. That's going to result in him having 2 more protons than he does his number of electrons. So beryllium here is going to end up with a positive 2 charge. Magnesium does the same thing. You can see he's got 2 electrons in his outermost shell right here. Since it is easier to achieve that stability by losing 2 electrons than trying to gain 6 of them, that's exactly what he's going to do. He's going to lose 2 electrons. So magnesium is always going to form a positive 2 ion. Now the reason we've got this gap right here is because that's where our transition metals are. Our transition metals can have varying numbers of valence electrons, so they can have different numbers of charges. So we jump all the way over to what is called column number 13. We can also just skip those transition metals and call it column number 3. Because there are 10 columns in that transition metal location. So if I take a look at boron and aluminum, which are in this column together, I can see that now the trend is continuing. I've got 3 valence electrons in both of these elements, aluminum and boron. And so again, it comes down to what takes less energy. Does it take more energy to lose 3 electrons, or does it take more energy to gain 5? Well, the answer is it's much easier to lose 3. So boron is going to get a positive 3 charge, and aluminum is going to get a positive 3 charge. Okay? Carbon over here wants to, he's got 4 valence electrons. So carbon is more of a sharer of his electrons, actually. So he is still going to need to get 4 electrons, but rather than giving them away, he's usually going to form a covalent compound, and he's going to share them. So he's still, regardless, he still needs to gain 4 electrons. So he is going to have the ability to bond with 4 different things. So this is why we often see methane as CH4, because carbon, he needs 4 more electrons. So he's going to share 1 with a hydrogen over here. He's going to share 1 electron with a hydrogen over here. He's going to share 1 with a hydrogen over here. And he's going to share 1 with a hydrogen over there. So he's going to share those electrons. He still needs 4. He likes to make 4 bonds. Carbon is going to make 4 bonds. Boron is going to need to give away 3 electrons. So for him, he's going to balance out charges with an ion. Silicon is typically going to get a positive 4 charge. He's not usually going to share them. Sometimes he will form covalent bonds with someone on the nonmetal side, which nonmetals are going to be all of these guys over on this side of the periodic table or over here in this image. Most of the guys, and actually I'm going to erase this little section here. These guys pretty much right in here are going to be all of your nonmetals. So if I bond a nonmetal with a nonmetal, we're going to talk about this in a minute, I'm going to get a covalent bond. Or if I've got 2 ions, a metal and a nonmetal, then I'm going to get an ionic bond. But we'll talk about that. Let's finish off our periodic table with our valence electrons. So nitrogen has 5 valence electrons. He's either got to lose all 5 or he just needs to gain 3. So again, think about the energy. He's going to gain 3 electrons. So he's going to get a -3 charge. Phosphorus is going to do the same thing. The trend continues on as we go across the periodic table. Oxygen has 6 valence electrons, 2, 4, 5, and 6. So if he gains 2 more electrons, it is a lot less energy than trying to lose all 6.